What's up, everybody? You are watching NASA in Silicon Valley Live for November 15th, 2018. I am your host, Matt Buffington, and joining me as a co-host for the first time ever is NASA's very own Tiffany Blake.
Hi.
It's Tiffany, for people who haven't seen your byline on nasa.gov, she's very famous. Go ahead and tell everybody, tell everybody what do you do at NASA?
Famous? Well, I work in the Office of Communications here at NASA Ames, and I cover all of our tech and engineering projects, as well as some of our mission activities. And so really I just help our people tell their story pretty much.
Awesome.
So yeah, that's exciting. You know.
And speaking of cool people that you talk to.
Yes, that I talk to. we have here Robin Beck and Paul Rosinski here joining us today. Can you guys tell us about yourselves, what you do here at Ames?
Well, my name is Robin Beck, and I'm a mechanical engineer from local schools. I grew up here, went to Santa Clara and to Stanford. So I work on heat shield materials, so anything to keep a spacecraft cool.
Mm-hmm. How fortuitous, since we're talking about heat shields.
What an amazing coincidence.
Paul, tell us about yourself.
Well, my name's Paul Rosinski. I am an engineer, currently a project manager out here at Ames, working in a group that designs heat shields, does all kinds of design and technology development, and I'm looking forward to telling you a little bit about my latest project.
See, Paul, if you didn't know, Paul is also super famous. We had like an old Facebook Live from about like a year or so ago that he talked a whole bunch about like, heat shields and gave us a tour of the arc jet. And Robin, you did a podcast episode a while back too.
I did.
See, Paul did another podcast episode that's in the can that'll be released sometime soon.
Oh, yeah.
We'll get to it.
We'll get to it later.
We promise. We did not forget you, Paul.
But folks, if you didn't know, this is NASA in Silicon Valley Live. It is a conversational show out of NASA's Ames Research Center here in Silicon Valley, where we talk to the various researchers, scientists, engineers, and all around cool people at NASA. And so if you like that, we are live on Twitch, on YouTube, Facebook, Periscope, everywhere that you can think of. But if you want to participate in the chat, you want to send Robin and Paul some questions, then you need to go to twitch.tv/NASA. If you're sitting on Facebook or YouTube, go back to twitch.tv/NASA. Send us all of your questions in if you want to talk to us live. If you can't catch us live, that is no big deal. We are also, we'll be up on Facebook, YouTube after the fact and on demand. We'll also be on, for our audio listeners, we'll be on podcast services throughout the solar system and beyond. But as promised, we're all about heat shields. So I guess we'll just start for the basic thing for people who may be watching who have no idea what a heat shield is. Let's just kind of go generic. Like, what is a heat shield?
Right. Well, if you have a spacecraft,
like a prop in front of us,
here, right?
Look at that.
And you're going to enter into a planet or back to Earth that has an atmosphere. It's going to be traveling really fast, and it's going to get really, really hot in the front. It's going to get pretty toasty on the back as well. So you want to protect the material. You want to protect the structure with heat shield materials. That's what it is. Shields from the heat.
So what kind of materials would you use to shield such heat? And
well, it really depends on how fast you're going, how big you are, what the atmosphere is. So there are a lot of examples. I brought props if you want to see some.
yeah, show us some of the cool stuff you got.
We got a lot of toys.
Let me put on my gloves because there's a lot of little particulates that I'd rather not have go get in my skin.
Get on
It
your
hurts.
Yeah, so folks, as we were rehearsing,
Sorry.
we've gone through a whole bunch of the different like products. You got some really cool stuff that we're going to check out.
This is real science and engineering.
This is a material that flew on Apollo.
Okay.
So, and it also flew on the first experimental flight for Orion, so our new vehicle.
And so we have a bunch of people. I'm sure you're going to tell us what it is, but people are going carbon fiber.
No.
They got Rhino Ranger and Guts Berserker Amor armor. We're saying that. So
No. It's
Not
not
carbon fiber.
no. But if you look up close, it is a honeycomb-based material. So the honeycomb gets bonded onto the heat shield, and then the stuff gets put in each cell individually.
Wow.
So that's how what this material is. And this can withstand heating easily up to 1,000 watts per square centimeter.
Oh, wow.
So this, this flew and came back from the moon. So we get some pretty high heating then. And so that's one that is very capable.
Okay.
Okay.
What you got next?
And if we go back to lighter heating, come back to Earth, we have shuttle tile material. So this is a coated shuttle tile, very, very lightweight.
It's almost looks like, it almost feels like a little bit like styrofoam
I know,
or
it
something.
does. Well, because it really is a foamed glass type material. So that's really what it looks like. It's very, very low density. The coating is so that you get, you re-radiate the heat rather than have it all come into the surface, because it turns out that when you have radiation, something that's white tends to absorb it. Something that's black tends to emit it. Right. So this will help the heat go away from the surface, but it's very, very useful in low heating conditions in keeping your structure cool.
Nice.
Excellent. So we have a bunch of people, the chat's going nuts.
Okay.
A lot of that's so cool, interesting. That's from Hannibal Zero. My buddy over in the chat, Nice Guy Dewey, was asking, what are major challenges faced in designing a reusable heat shield? Because most of this stuff that you're looking at is like, it's a one-time use, right?
The shuttle material, the tile
well,
is
obviously
not.
that's
Right.
yeah.
But the other ones are
multiple.
because they're ablatives.
There goes the A word.
They're A-word.
So, folks, yeah, like, as we had talked about this, we kept talking about ablative. Like, you can't talk about heat shields without saying ablative. So,
Right.
so we're going to just come out. Like, so let's talk about ablative. What does that mean?
Okay.
That most people don't
Right.
probably don't know what that is.
Well, we can turn shuttle tile into an ablator, but what it is you have a rigid or a flexible substrate that gets impregnated with the resin, and that resin decomposes when it gets hot, and it uses a lot of the energy to decompose, which is great because using that energy keeps the energy from conducting to the structure. So it also interacts with the boundary layer, which is what's heating up the surface and makes it a little thicker, which reduces the heating. The fact that it's creating gases blows through the char layer that's left there, and it self-cools. So it's a really efficient way of keeping your spacecraft cool. The problem is that it is changing state, and other than making it super, super thick and then shaving off the char layer and getting back to virgin material each time, it's really not reusable. There are some companies that are looking at reusing a Pika-like material, which is what I'll show you next.
Nice. Yeah, let's jump into the
show us.
Pika Pika.
Yes, Pika Pika.
Okay, so this material was invented here, as a matter of fact, and it's based on a rigid carbon structure, so that's really tough, right? And it gets impregnated with a resin. Okay, so Pika stands for phenolic impregnated carbon ablator. Carbon, the yellow is phenolic, turns it this kind of color. So this is great.
I'm going to have to jump into phenolic. What does that mean?
Phenolic is a resin. It's a
it's
name
just
of a resin.
It's a name of a resin.
Right, like silicone is a resin, which we also use, but phenolic is a very, very good resin because it uses up a lot of energy to decompose. So this is great. This material in tile form flew on MSL, which delivered Curiosity. It also will fly on Mars 2020, which will deliver the next rover to Mars. It flew in single piece on Stardust, and it's flying right now on OSIRIS-REx in a single piece.
So as we were practicing and rehearsing this, I kept saying that the chat was going to go nuts with Pika Pika. So Anthony is me. He's got a good Pikachu emote going on. So you guys aren't letting me down. But I was expecting more, to be honest. So all right,
at least it's yellow. Okay, so
it is yellow.
Ish. So the good news is that it's a great ablator. The bad news is it's very, very brittle. So it makes it a little bit difficult to design with. So we've been working on an advanced version of that.
So this is a new heat shield material?
This is a new heat shield material that is based on carbon felt, which is flexible.
Okay.
See? So we take that. Now, once we impregnate it with about the same recipe, It becomes rigid. It's not going anywhere. But we can mold it before we impregnate. We take this felt, we mold it, and then we
Shape you
impregnate,
want.
and so we get the best properties everywhere rather than just along certain lines of a tile. So it's near net shape. You can see, we can machine it and machine plugs out of it, all kinds of stuff. So then the even better news is that it's even more thermally efficient than Pica is. It weighs about the same, very lightweight, weighs about the same, but it's even better than Pica.
So a couple shout outs from Pumpkin Pie. We're seeing you, dude. He was saying, this is epic. Mr. Heat Shield Girl is saying just a big old Pica. So a lot of shout outs for that stuff. And then I was going to say, I saw one that came in from Ztron, was just saying, is it structurally bonded, not chemically? Does that sound right? Yeah.
Yes, it is. It is bonded with an adhesive to a structure.
And so it makes it more efficient.
Which?
Or the last one you just showed us.
Right, it's more efficient only because it's more efficient because of it. Well, we can make bigger tiles,
right?
And we also can bond directly to an aeroshell, where in some cases, Pica might need strain isolation pad, which is what they put under shuttle tiles. They put a strain isolation pad behind the thermal protection material. And it is more compliant, so that's one of the benefits of the conformal. We call it conformal Pica because it is more compliant.
And this is one of the crazy things as we've been talking about this of, ablation and then these heat shields, because it's like you're building these out of material, but it's also like you pick the properties that you expect them to not really burn up, but it's like they get a char. They're going to get a little bit of cooked.
And they actually do burn out. I mean, they go away. They get thinner. So that char...
and it's by design.
Absolutely. Absolutely. And what you do is you protect the structure. So you design it so that, the temperature at the bond line doesn't get too hot, right? You don't overheat your structure. So we understand we can model these kinds of materials and we understand how they behave. And so that's how we use them.
It's amazing.
It's pretty cool stuff.
Right.
So
what
else do you have for us?
Our latest?
Yes.
Is that what we're doing?
Yes.
Our latest material?
Go for it.
Right? Okay. Our latest material is called, it's HIAD with many E's. Three E's. Three E's, you can see there. And this material is I'm going to set it down, a 3D woven material. So you imagine a large loom, like you're, making cloth, but this is making cloth in 3 dimensions. And we can take advantage of having a higher conductivity, higher density, higher capability, ablative layer, receding layer, over an insulating layer, and it's all integral. We don't have to worry about how do we hold those 2 layers together. We looked at but they're woven together layer by layer, so we don't get any interlaminar separation where you would in a tape wrap type carbon phenolic heat shield. So, and it's tailorable for how thick you make the insulation, how thick you make the recession layer, and what the densities are. So it's a very, very cool material. But this is for very high intensity environments. You wouldn't use this going to Mars. You don't need it. But you do need it going to places like Venus if you're doing a very sharp direct entry.
No, we got a couple of questions of I got here, what's up with the gloves? That's a hit cell. And then I got several comments on the gloves. And so maybe just clarify. I know you said it initially, but talk about why you're wearing the gloves.
Well, Pica has a lot of, watch, you'll see, I'll get yellow on myself and on the table. The phenolic comes out.
Okay. It just gets sloppy.
Right.
It leaves
and a lot of there's carbon fibers in the felt, and there's carbon fibers in the rigid substrate. So I kind of don't want to stick it in my fingers, or I don't want to touch my face after I've had my hands on these. So it's
Safety
just
first.
to kind of protect. Yeah, exactly.
Something else I wanted to just point out is, with all these materials, the temperature gradient that it sees across the thickness. So on the hot side, that surface can be seeing several thousand degrees, but just a half an inch or an inch away, it's at just a few hundred degrees. I mean,
Exactly.
and that's
Wow.
what's really amazing about all these materials is
Right, it's a very steep gradient. They're insulating materials, a very steep gradient through them, thermal gradient through them. You know, we have to protect that structure, and that structure could be something like aluminum. It can take a lot of temperature. It can also be a composite. I mean, there's a lot of limitations now
protected.
how hot this back wall is. And what happens with this material is it's very similar to Pika in that, or similar to the conformal Pika in that we take the woven structure and we mold it. So this was flat when it was woven, and we put it over a mold because it is, it's thick, but it's stiff, but it is cloth, and then we impregnate it so it's a near net shape. Now this has been machined, but this is a near net shape.
And we were talking about it, like these are woven materials, and I was kind of like, what is this, like a big mechanical loom? And we're like,
Absolutely.
that's exactly what it is.
Exactly what it is, yes.
is this like sitting somewhere in a warehouse? You have this big
Oh,
loom?
no, no,
It's like,
we don't do this.
We're not doing that.
Right.
No.
There's a company in Pennsylvania that is weaving for us, and they started out weaving ribbons.
Okay.
Ribbons for hats, and they
Now
now
they're
are
doing heat
weaving.
shields.
Yeah.
Yep, they're weaving heat shields. They weave protective materials and other stuff too. But yep, they're weaving stuff that's going to space.
Wow. So I have a question.
Sure.
Basically, we need different heat shields for different missions.
Correct.
Right? So say I was going to Mars or I was going to Earth. Like, what kinds of different heat shields would I use for, to re-enter Earth or to land on Mars?
Right. Well, the Apollo type material, the Avcoat that I showed, would be easily coming back from the moon, going into the Earth's atmosphere. You don't need it to go to Mars. Pika is perfect. It's even a little better than it needs to be, to go to Mars, because the heating there, our peak heating there on our heat shields is about 200 watts per square centimeter. Coming back from the moon, we're over 600 to 1,000 watts per square centimeter. Going to Venus, we can be as high as 5,000 watts per square centimeter, maybe even higher than that. We need things like heat. So it really depends on what your atmosphere is.
And the whole reason of all that is you don't want to carry every ounce, every kilogram is
Matters.
precious. So
Right.
you don't want your heat shield to weigh any more than it has to,
to.
because that's taking away mass that you can be doing science or something else with.
Right, your
Right.
payload, it gets reduced.
So, and going on along that line of like Venus and especially for Mars, we have two questions. One came from a man called Steve for how more advanced is the heat shield for new rover for Mars 2020? And similarly, Mr. Heat Shield Girl said Mars 2020 heat shield is the same as Curiosity heat shield, I think.
Yes,
So
it
talk
is.
a little bit about that.
It is exactly the same. And so we've just been making Pika. We've started there machining the tiles. We're, to save money, didn't want to redesign, right? So you wanted to use as much of the design from MSL, which delivered Curiosity. You wanted to use the same design as much as you could possible. So there are 27 different tile designs on that heat shield. So you didn't want to have to start over and redesign. There are 113 tiles on the heat shield. So if you had to figure out a new tile layout and change the thickness, for example,
That's a lot.
which we definitely could, it's very heavily over-designed, but it didn't make sense cost-wise to spend that money to do that again.
And so I want to come on over to one of the questions from Rye Oranger is asking, and this is a pivot to, we can't talk about heat shields without talking about the arc jet, because their
Right.
question goes
Haven't
into
tested.
how are heat shields materials tested, and can you replicate temps in a lab that are seen in production? Paul, I know you gave me the tour of the arc jet at one point,
Yeah.
so...
Well, the ArcJet is an incredible facility, and sort of the easiest way to explain it is think of a wind tunnel that has as its reservoir a tank that gets filled with high pressure, high temperature gas. They blast literally a lightning bolt through it to energize it and give it that much more energy.
Make it that much hotter.
And then they just open up a nozzle at one end, and this high temperature, high pressure gas just goes blasting out. Mach 5, Mach 7, it flows over your test article, and they take all this energy, all this electricity that can literally power a small town, And all that energy gets concentrated into a small test. I mean, it gives you an idea of just what type of environments these materials have to be designed for.
Basically,
So
yeah,
it
it's lightning
simulates.
Yeah.
It simulates
simulates the environment.
re-entry into an.
We tend to test
entry into an atmosphere.
Right. We tend to test in air. However, we can get the right heating rates, and we can get the right pressures. If we need to, we can get the right shear.
Sheer, like, what is.
Shear is the friction, the flow over.
Okay.
So I have an arc jet specimen.
Let's go for it.
And I took my gloves off.
I think we actually, Bill, I think we have a clip of this
We
too
do.
as well.
Yeah, we have some fancy
Okay, that's
footage.
right. You can watch.
Yeah.
Oh, it's an
Of a
arc jet
test.
It's an
action
arc
here.
jet specimen going into the facility.
Yeah, tell us what we're looking
Yeah.
at.
So this is a sphere cone.
Oh.
This is the heating at the nose on this test article is 700 watts per square centimeter.
The flow's coming from the
It's
top,
coming from the top
down,
down,
flowing over it.
Right, and on the flank, on the conical part of it, the heating is 400 watts per square centimeter, and then the shear around near the shoulder, near the back side, the back end of this, is 400 pascals, which is a lot. It's similar to what we would see on Mars 2020 and MSL. So we were looking for a test article design that could do that. Now,
Yeah, and I was going to say, that footage that we saw,
is this test article.
that is the exact same
Correct.
thing.
Wow.
And this test article actually was testing, we have pica on here, and we have the conformal pica with seams and gaps. So we were looking at, could we put the material right up next to it without needing to design for gaps? And it turns out, yes, we could. And we also were comparing the recession, so how much thickness we lost. We were comparing the recession to that of pica, and it's very, very comparable. It's about the same density and very comparable recession. The best news was that the temperature rise at the bond line was half of what the temperature rise at the bond line behind the standard pica. So behind the conformal pica, it's much more thermally efficient because the conductivity is so much lower. So
And I think, Paul, you told us yesterday that that's what you guys want to see after you have a test.
Oh, yeah.
Right? You want to see it all burned up
Right.
and
Right. Well, you do have pictures of
Yes,
a
we
before
do.
and an after
We do.
of that test article. And so if there it was yellow.
The original.
Yeah, that's the original. And what you're looking at is the conformal. The nose is actually pica and then one quadrant, which you're not seeing here. But then after, it looks like black. And that's the same test article. So,
Wow.
Right. So it changed shape slightly. You can tell the nose blunted up because some of the material went away, but it charred and turned to carbon.
And there's not a whole lot of in between in these tests. They either work right or they just fail completely. I mean, because
Tell
as soon
me
as
how spectacularly they failed. I want to
I mean, literally within a fraction of a second,
Second,
the whole thing will start falling apart, and
Oh, no.
they stop
wow.
the test right
Yeah.
away. I mean,
Yeah, we
That's
had
pretty-
some surprise tests, not on this material, but we had some surprise tests on some materials in areas in heating rates that we didn't expect to see problems, and we had material absolutely disappear in 4 seconds where it shouldn't have. So
well, and also just to give people some perspective, I mean, if that same test article was just the same piece of aluminum, and you put it in there,
it'd be
it
gone.
would last in a fraction of a second, and
Right.
the whole thing would be gone. I mean, that just
Right.
gives you an idea of just the energy and the temperatures that it sees.
right, the surface temperatures here were between 3,000 and 4,000 Fahrenheit. So at the nose, it was about over 4,000 Fahrenheit, and on the flank, it was at 3,000 Fahrenheit.
So you might as well be walking on the sun.
Not quite. The sun is about 10,000 Fahrenheit, but it's pretty darn hot.
Yeah.
And how long are you guys testing?
That one was in for 30 seconds.
Ah, okay.
And a lot of that
And they
just
vary,
depends
right?
on the trajectory, how it's going to fly at its destination planet.
Right. We were trying to match the heat load, which is heating rate times the time. So as we went to lower heating rates, we went to longer times.
Oh, I see.
So the chat is going completely nuts. We got a shout out to the ArcJet team. This is from GR_AB. We got a couple questions. One that I just saw through go live. This is 4th and Inches 1. It said something similar to the same thing that another person asked about the heat panels on Parker Solar Probe. Is that how that works? Or
The same thing. I mean,
Okay.
they're protecting it's a carbon material. It's all carbon, and it's so it can take very, very high energy and has insulation on the backside so that what's behind it doesn't get too hot.
And that's a pure radiative heating because that's
Pure
from the
radiative
sun.
heating, right? Right.
And so also another person who jumped in the chat is Scott Manley, one of our co-hosts. Last time we did one of the shows a couple episodes back, he was asking, and welcome back, Scott. Nice to see you. Can you tell us about the most extreme heat shield NASA ever made, like the Jupiter Atmosphere Probe?
Oh, yeah.
Yeah.
Galileo,
The
yeah.
Galileo, yeah.
So talk about that. Paul, what do you
Well, that was a mission that flew into Jupiter, and Jupiter is a hydrogen-helium atmosphere. So back in the day, they literally had an arc jet that used hydrogen-helium.
Right.
And they had to blast so much energy that they were able to not only get the convective heating, but the radiative heating that you would see at the high speed. So entry into Jupiter is this outlier that's far away from all the other entries.
Beyond
And so,
10,000 watts per square
and
centimeter.
But it's got to be fun.
It's really, really high.
So they
Fun to
did
work
those
on.
tests. That facility was up and running, I think, in the 70s and in the 80s. They did the final designs on the heat shield, but that was a probe where half of the entry mass, half of the probe mass going into Jupiter was all heat shield.
Right.
And they actually, because they did some measurements, but they came pretty darn close to losing it with some of the measurements, because they were able to tell in certain places on it how far it recessed. And there were a couple places where they realized there wasn't a whole lot left after it finished the heating pulse.
Right, and it
Wow.
was the opposite of what they expected. The nose receded less than they expected, which is the highest heating, and the flank receded almost all the way through.
Wow.
Yep,
I'm
that's
gonna
right.
jump. I'm
pretty
gonna
close.
jump.
Okay, right, yeah.
I'm gonna jump in because the president of Mars, and if the president of Mars
Oh, you
is
better-
typing
yeah,
in,
you
we have to
better
respond.
listen.
It's what kind of fibers are used? What kind of properties do the resins have? And how are they manufactured, handled? That's a lot to unpack.
Wow.
Most of the fibers, well, the Pica
I guess it
fibers, that's
depends.
carbon,
Yeah,
right?
yeah.
Those are carbon fibers, rayon-based carbon fibers, and the phenolic is a phenolic resin, which they use, I think, actually in brake pads too. So it's a common resin. It's so, but and how are they manufactured? That's a secret.
Actually, I'm sure it always depends.
Yeah. Well, it does. It really does depend on what kind of density you want and what kind of properties you want.
I'd say re-entry into Earth is different from entry into Mars,
Mars,
or into
yeah.
Venus. It's like
Right.
different test
It depends.
conditions.
Right.
We were talking. It depends.
It depends.
We
I
love to
know.
say that
The
here.
ongoing
That's
joke for
right,
everything is that it
right.
depends.
It does.
It
does
depends.
So, oh man, like this chat is insane. There's so much stuff going on. So, let me jump to. Let's say, okay, hi NASA. Does the shape or angle of the heat shield affect how thick it has to be? That's from
Yes.
Brad McGashett.
Yes, it does. It affects the heating profile, and so we've typically flown to Mars with a 70-degree sphere cone, which is what MSL and Viking. I mean, everything that's flown to Mars, I think, has been a 70-degree sphere cone, a blunt body. The Venus, we flew with 45-degree sphere cones, and it definitely affects what the heating on the material is, and the thickness is dependent on what the heating on the material is.
It's funny because I feel like we could sit here and talk this all
forever.
day.
Right.
Even
There's
and clearly, like the chat can talk all day about this as well. There was a
Absolutely.
question that came in from Raj 2017. What about inflatable heat shields? And I thought that might be a good transition to some of the other stuff. And I'm also looking at Tiffany, who makes
How you
sure
do
that
on
I'm on
time.
track
Yeah.
on
Yeah.
the things that we need to talk about. Are we
Yes.
going to pivot over?
Yeah, no, I think we could take or we can. Sure.
We can, yeah.
You tell me.
Well, I mean, we've been talking about a lot about Mars too, and so I know the agency we're all excited about InSight landing in a
coming.
couple of weeks.
Yeah.
Scheduled for Monday, November 26th.
Which happens to be Cyber Monday
Yes.
after everybody's in their turkey coma.
But it is landing at basically lunchtime. It's 11:47 a.m. PT.
Yeah,
So
Pacific
you know,
time.
Pacific time,
You guys
right.
get grab your lunch and then watch the NASA TV. But wanted to ask you guys, can you talk a little bit about InSight and
Sure,
what
it's
we
a
can look forward to in a
lander.
couple weeks?
The TPS, the thermal protection material.
So this is actually on
this
InSight.
is what's on the
That's
heat
actually
shield.
what's on it.
This material is on the heat shield. The heat shield is thicker than this. This material is also the back shell for MSL and Mars 2020 at about that thickness.
Makes sense. You have to heat the front and the back because the
You
back is
do,
going to...
absolutely. You heat both.
So Insight is like half the size. It's smaller.
About half the size. It's not going in as hot and or as fast. It's lighter weight. And so this material is perfectly designed. It's what's always flown to Mars on our U.S. spacecraft, except for MSL. So the MSL was so large we couldn't.
MSL, we love acronyms here.
MSL is Mars Science Laboratory, and that delivered Curiosity. So Mars 2020 is coming. It will also have this material on the back shell and Pika on the heat shield because of the environment. So,
and so what's InSight's mission? What will the lander be doing on Mars?
the lander will be measuring the temperature through the thickness of the shell of the, of the planet.
Yeah.
And it will also be measuring seismic activity. So there's a thermal probe that'll go down about 6 meters, so 16, 17 feet or so. And there's a seismometer that'll sit on the surface and will measure Mars quakes.
Mars quakes. And I think we have a clip here.
Right, of the
showing
entry.
us,
Right.
Yeah.
Yeah, let's like talk our way through this.
There we go. So that it's right now it's got the cruise stage, so that's been let go. And now that you have the entry vehicle, kind of looks like our little model there. Now it's getting very hot on the front, but also that wake is radiating to the back shell, and so we have to protect it as well. And then eventually we slow down enough that we will pop a chute to slow it down the rest of the way, or nearly the rest of the way.
Which is interesting because Mars doesn't have as much atmosphere.
No, it doesn't. It's very difficult to slow down. So as soon as we pop the chute, soon after that, heat shield gets dropped because we really want to deploy this lander. So the feet come out, then it'll drop out of the back shell, and that will kind of fly away. And the lander itself will propel itself downward, or use propulsion in the opposite direction to slow itself down.
A controlled descent.
Yeah, it's a controlled
And
descent.
in the chat, Tom it was asked, InSight doesn't move, correct? Because you said lander,
It's
not
a
a
lander,
rover.
exactly. Look, there's no wheels. So this is because it lands near the poles and it doesn't have to move. It is powered by solar power. It's not nuclear powered like Curiosity is. And so it will sit there, and it has a 2-year mission. So, and gathering data. They do expect, they know that Mars gets hit a lot with asteroids and foreign bodies. And so the seismic equipment should be able to measure the impacts as well.
Wow.
And so sadly to Pogu_, that was not live footage.
No.
But we do have
no.
not live footage. We have some footage of some of this fun stuff that Paul's been working on.
Right.
Am I
Yes.
spoiling it? Am I jumping too early?
Yes, a little bit.
All right,
You
go
know,
on.
we do want to tell the folks, for more information about InSight, you can go to mars.nasa.gov/insight and make sure you tune in on the 26th to see that exciting land.
And then I'd also throw out a reminder for folks who are watching. If you're watching on Facebook, YouTube, Twitch, we are live right now. But if you want to participate live on the chat, you need to go to twitch.tv/NASA. We have a ton of questions coming in, and you're in luck because about the last 10 minutes we're going to spend doing rapid fire questions. We're not there yet, and we're going to try to hit as many of these as humanly possible because there's so much going on in there. But go for it.
So we know that heat shield development continues to evolve, right? And so I know, Paul, you're working on a project that really dives into next generation heat shields and game-changing technology. So tell us a little bit about ADEPT. What's ADEPT?
Well, ADEPT is another one of these great
Acronyms.
Adaptable, deployable, entry and placement technology. So that's a mouthful. And the way we try to describe it is up to now, what we've been talking about are heat shields that we call rigid heat shields. So it's a solid structure, able to take high temperatures, but it's rigid. So what you launch is what enters the planet. And what we have seen is there's a lot of missions out there that could do more if they could be launched with a heat shield that opened up to even bigger sizes. And right now, what's limiting the size of our heat shields is the rocket that carries them. So if there was a way to make a heat shield that could fold up or stow and then open up once it's free and clear of the rocket. We could do more things, go to do more science. So that's what a depth is. Think of a heat shield that works like an umbrella. So I got something I can show you too.
Yes, show us, please.
Clear the decks here.
Yeah, I'll move this out of your way. And folks might have recognized what Paul's going to show out if you watched our Halloween episode.
Yes.
That Mary Techno Poppins had a version of this.
Yeah.
And Paul
There
was
it
out
is.
here. Paul's super famous, as I mentioned before.
Yeah. We all have to do things like that.
So this is exactly what it looks like.
Yeah, so this is an umbrella. It literally has, you can see underneath it. Whoa, there we go. It's got ribs and struts underneath it. This is a flexible carbon fabric. This is sort of related to the woven material Robin was showing, but this is not impregnated. It is just 4 to 8 layers of carbon fabric woven three-dimensionally. So when this does get glowing hot, and I think we're going to show some video of this maybe, when we test this in the heat shield or in the arc jets, glows red hot, survives for 1 to 2 minutes. Now what we're seeing here is the same size, is just under 1 meter diameter. This is a heat shield that we flew on a sounding rocket a few months back.
A few months ago, I was there.
You were there.
So also in the
Super
chat,
exciting.
a good friend Das Valdez is sitting in the chat. So hi Das, how's it going? And he mentioned there's a video game I told you guys about called Kerbal Space Program. But he was saying that like in Kerbal you can actually that there's an adept in there. There's like deployable like heat shields. So the next time we do a gaming episode, we'll need to bring you on over. And Das, you should come on out, and then we could totally hit up, start putting adept on some rockets.
Wow.
That's so cool.
Right, so when this is launched, it's all closed up, so
Yeah,
the
it's
sides
stowed,
are straight
right?
down, right?
We could
You
even
can
try
push
to
a little
pull it
bit.
down
Yeah, they're
there. Let's see if
pretty
we can,
hard springs.
I got to find a rib here.
He's got to work his arms out as he
Go,
pushes
Paul,
it
go.
down.
Yes, there we go.
So it starts that way, and then it is deployed
This
in
is just a demo
space.
model
Right,
here, so-
right. It's deployed in space, so it doesn't have to do anything really fast, right? It can deploy slowly in the exoatmosphere. So
Awesome.
it's an awesome idea. Now, we did have a question, someone about inflatables, and we do have a very similar approach for an inflatable. So it's
Heat
another
shield.
deployable heat shield,
Another way
but
of doing it,
it's inflated, and so there are large toroids that are being built in Southern California that get stacked up with thermal protection materials on the outside, and they get squished even smaller, and then have all kinds of devices and gas generators to deploy them.
Are we going to jump into the
So-
footage?
Yeah. So we were
your
in New
test?
Mexico a couple of months ago, right, Paul?
That's right.
This is your first test flight for Adept.
Right. It was just about the same size. This is, like I said, just under 1 meter in diameter.
So here's the
It
rocket.
folds up into a rocket with a 10-inch diameter tube.
And get ready for some cool GoPro footage.
Oh,
Yeah.
man.
So that was
So there's a launch, and it's within 10 seconds, it's already leaving the atmosphere. And within a minute, it's up at about 100 kilometers up.
and then
And there
Boom, there it goes.
display.
We're just reaching our maximum altitude around 120 kilometers. We've opened up, and now with a GoPro camera on board,
Notice that curvature.
we are confirming that we
It's a
opened up.
disc.
That was one of our major objectives of the test, was to show that we can deploy. And now, as we're descending into the atmosphere, we got all these instruments recording how it's the aerodynamic stability, its flight attitude, rates, all this good information that we're now still poring over and deciphering.
And it was supposed to be spinning, right? I mean, it was spun
Yes.
up out of the rocket.
Oh yes,
So
that
it was supposed
part
to be
of
spinning.
what it needed for
That
stability.
was on purpose.
Yeah, that was on purpose.
Yeah.
So how long does it take to, get from the start to your first flight test?
Oh, well, we've been working, the ADEPT project has been active now for, at least 6 or 7 years. The last 2 years, I'd say we were hard at work on the sounding rocket flight test. Up to then, we had been doing a bunch of ground tests. We've gone in wind tunnels. We've gone in the arc jets. We've done all different kinds of tests to try to understand and make sure we're confident in how this new heat shield can perform. But then ultimately, like with a lot of things that go into space, people will only believe it when it flies in space, and so that's that was part of our purpose of this flight test, and it did what we wanted to do. And then we're hoping down the road to even do some more adventurous flight tests coming in from orbit to where we'll actually see heating, that you'll see in an actual mission, and that's how we'll really get higher confidence in this.
So those are like the next steps for Adept.
We hope so.
Too.
Yeah, absolutely.
Awesome. I know when I was there with you guys, just seeing the team together, start, prepping, getting, Adept into, like, it's stowed into the rocket and things like that. And you can't believe it's like really in the rocket, but when you see it, like it's
your
stuffed
Super
in
Bowl.
there.
Yeah, absolutely.
So you get to see the team, and he has a really great team, and just like their interactions and just how they finally got to like their first flight test. It's really, really cool.
And Paul running out with his.
Also, I remember when you guys were retrieving Adept after the test, they just like everybody jumped into an SUV and like drove off. There were almost skid marks in the desert.
They're like,
sand.
go.
They're like, go.
Well, we were at this is at White Sands Missile Range. It's an Army base, and they had all kinds of other activities going on that same day, and so the recovery crew was in the helicopter was, coming and going all over. They couldn't tell us exactly when they were going to come to do our part of the mission, and so they said just be ready at any time. And so sure enough, 4 hours later, get a knock on the door. You guys got 3 minutes. Get out to the helicopter. And we're like, okay. And so we were scrambling.
Yeah, we're literally
the,
looking out the window like, oh my gosh, they're gone.
Are we going to show the footage of them?
Yes, we have some really cool footage of Paul getting
Look
out
at
the
that.
But this is after
helicopter.
we've recovered out in the desert.
And so the test is about how long?
Well, it takes only about 15 minutes from launch to coming back down on the ground.
Oh, there he is.
Yeah, so very relieved, very happy. The Adept took a hard landing. We were expecting that, and so that was the container we put it in. And the team is still working on, we've recovered all the data from it. It stored all the data on board on these little memory boards. And we've probably got a few more months worth of deciphering and analysis to go.
So one question that came in, this is from Selenu here. This is seriously though, can you buy this carbon fabric somewhere? It's funny because it feels almost like a backpack a little bit.
But
The little
really
straps on the
A
back.
really big
Yeah.
backpack, and probably an expensive backpack.
Yeah, well, I mean, you'd have to probably talk to the manufacturer about Bally Ribbon Mills and see what they want to charge you. No, I mean, it's very specialized. I mean, it's for high temperature use, but it's very durable, very rugged, and that's what makes it exciting as a heat shield material because it can take a lot.
So, okay, let me jump on to some of these chat questions. We are going to do a rapid fire towards the end, but let's go into, all right, what sort of properties would the rocket need to support that kind of dynamic heat shield as opposed to a rigid one?
No difference. I mean, I think
it's just lighter. Like,
well,
for us.
the nice thing about it is that you can take the same payload in a much smaller rocket because now you're not dominated by this huge heat shield, a rigid heat shield. Now it can all fold up around your payload. So.
And also shout out, that was Harold with an H. I forgot to give him the shout out.
Well, the one thing too, though, is it as it gets bigger, it's not necessarily going to be any lighter, right, than the current heat shields. With all the structure and the cloth is not, really lightweight either. So, I mean, it's not so much weight, it's volume, and you can put much more volume in and have it open into something so much larger than what we're using for Mars 2020. And we're really getting to the limits there with a 4.5 meter heat shield on what can fit in our fairings. So
and what you can land.
What you can land,
So
right?
we are getting shout outs for anyone else think that there should be a Paul action figure.
Oh, I know.
And then Rhino Ranger said, as long as the figurine comes with a heat shield.
There you go.
Very cool.
So you should talk to Lego. We need a Lego Paul.
I think that the headphones from the,
Hey, I did build one of these out of Legos, by the way.
really?
Yeah.
And you should have brought that. That would have been a better product.
Well, it's been taken apart. I'd have to put it back together again. But yeah, no, that was something we built about a year ago. It was pretty fun.
Awesome.
Yep.
I don't know. That was so cool. I think that really was like the highlight of my career so far.
But here's a question for bloodthirsty cheeseburger. How many people does it take to design, develop, and install this unit, Adept?
Well, you know,
Takes a village.
It does. You know, we had a fairly small team that was working on SR1, but we had probably on total, say, roughly a dozen people, more or less full time, working it over a year or two.
Okay.
Just for this test,
Just for the
right?
test.
The design, the preliminary designs over the last few years has been, a lot of people working, and designers and analysts and people for doing all the instrumentation.
So I think, Paul, you mentioned to me that it took a long time just to get the fabric right, to find the material that you needed.
The first couple of years, all we were worrying about was how to weave the fabric and how the layers would get set up. We weren't even sure that was going to work. And so we had to prove to ourselves that a fabric could take the loads, because that's what's a little different of this than even a rigid is. Now you have this fabric that's being pulled while it's glowing at 3,000 degrees Fahrenheit. So it's got its work cut out for it.
So a quick reminder to the folks, we're going to do rapid fire in the next little bit, but we're at twitch.tv/NASA. If you have any questions, jump into the chat now to add those. Like our friend Jennifer, who's put in a couple of questions over and over, and the latest one was, are these heat shields tested in vacuums? And evidently, I think Jen is a friend of yours, Robin. She was like,
I know Jenna.
She was like, if you can tell Robin, Jenna says hi. She's a good family friend.
She's a student down at University of San Diego, University of California, San Diego. So
I mean, I guess you can control what kind of environments you want to test these in.
The ArcJet typically is tested. Usually, we test in very low pressure. In vacuum, we don't get heat. We get radiant heating. But it's not very high. We get solar, right, as we're going through space. So we do have to design our spacecraft for this heating from the sun as it's traveling.
I guess if you're going through an atmosphere, it's no longer a vacuum.
Exactly.
Yeah, that's right. Exactly.
But, it is low pressure.
Okay.
So we do test at, we do put it into a vacuum chamber and then flow the gases over it. And that helps the gas to expand and to get to the right pressure, right, through the nozzle. It goes through the nozzle and expands and goes over our test article.
So I know I went to TwitchCon those last couple of weekends ago, and I know that several people would be interested. And if you've seen the YouTube show where they do the hydraulic press where they crush things, imagine a show where we just put things in the ArcJet.
Oh, wow.
I'm gonna guess probably not.
When we were working MSL, one of our guys wanted to make a meat shield.
A meat shield?
Barbecue.
And different,
like that.
right? And different meats, and
I would
see
watch
how
that.
they would cook. And you could only do them really short time. But was Kobe beef different from
Bacon.
American beef and pork and stuff? So we did have one person who wanted to test a meat shield.
Wow.
A shout out to Space Master. He asked before, how do I watch this show live? You are watching this show live right at this moment.
Right
and he also
now.
gave a shout out to Gary Jordan, who's over at Johnson, because he says that he's friends with Gary. I do know Gary. He's a cool guy over at Johnson. But we're going to keep going to a couple more questions. And I'm going to look at, can such a shield cover objects with irregular shapes like a decommissioned satellite? That's from Baba Keys. I don't know.
Well,
irregular shapes. What kind of crazy shapes are you looking for heat shields? Or for the most part,
well, that's one of the things
dish.
they're talking about with Adept is as recovering satellites, small sats, right? Instead of just having them burn up as they come into the atmosphere, actually recovering. So, or from shuttles, not shuttles, from space station, doing down mass, right? Sending experiments down. And so they're looking at things that start small and can deploy outside of the space station so they don't take up as much space. But could they send down experiments, right? And be able to recover them fast enough to look at the data. So, and they are, we look at these as for small sats as well, for small satellites to enter atmospheres and then to go into orbit around them.
And so one question for Paul that came in from Cats Love Mars. But this is also, we just kind of brushed over it. We showed the sounding rocket. And so Cats Love Mars was asking, what is a sounding rocket? So how is that different from a normal rocket?
Well, I think generally a sounding rocket is where it just goes literally up and then it comes back down. So it doesn't have the oomph that bigger rockets have that would put a payload into orbit. And so sounding rocket, I think, goes back to the days when they were just trying to study the atmosphere. So they would just send instruments sort of straight up, and they would measure some at some altitude, take some measurements, but then come back down.
Awesome.
Tiffany, is there anything you want to hit before we go to rapid
I think
fire?
we should speed it up and go into rapid
All
fire.
right, but I'm going to have Eric open up the audio for Bill and Dave over in our control room. Guys, are you guys ready to rock and roll for some rapid fire?
I'm in the mood for some rapid fire.
Go ahead and roll the thing.
We have and a heat shield. There you go.
See, we were not going to waste that animation.
Not at all,
We were
man.
going to use it.
That's a heat shield.
As we
right?
learned when we were
appreciate
practicing rapid fire, sometimes rapid fire isn't so rapid.
Yes.
Really.
But we're going to try it, and I'm going to grab
answers.
some of the latest ones and kind of move our way up. Okay, what part of the heat shield gets hottest? That's from Tombit.
Oh, usually it's this part right up here, the
All right.
stagnation. We call that the stagnation point.
All right, is there an estimation of how much money is worth investigating in more research and material cost to lose 1 kilogram of weight? That's from Zapfits.
1 kilogram, not so much, but half the TPS weight, definitely. And again, it depends on where you're
As
going,
always.
on what kind of heat shield you need, and on how heavy it will actually be.
Okay, so what material is the disc on top for Adept? This is Invincible Moon.
Oh, well, what we're looking at for this guy right here, this is literally stainless steel, and this is some 3D printed plastic, because this is a demo model. But what flew for SR1 was a metal nose, and we got away with that because we only flew to Mach 3, so we didn't see real aerothermal heating.
Only Mach 3, whatever.
Yeah, just barely
It's not
got
very
the paint
fast,
warm.
right? But for planetary entry, they're actually looking at flying with conformal Pika.
Yep.
Right on. There's their Pika Pika again.
There's your Pika
I know,
Pika.
you guys,
Yeah.
you guys in the emotes, don't let me down. All right, we're going to keep moving. So are there any other cooling systems that work with the heat shield for Adept? This is star molds.
Cooling systems. Well, we've looked at, one of the challenges with this is the fabric gets red hot, and that's great because it's carbon material, it holds together. What you want to do, though, is be careful with things underneath it that are also going to get hot just because they're close to the fabric.
Yeah.
So we've looked at insulating materials that can go underneath the ribs, sort of between the ribs and the fabric, to help keep that heat away.
And then also on the payload itself, some sort of blanket on the payload to keep it from getting radiantly heated from the back side of the carbon.
All right, some are coming in. I have old questions and we have new. Oh my gosh, it's coming in.
Rapid, come on.
What is the multi-layer insulation made of? That's our buddy, nice guy Dewey again.
Oh, the multi-layer, it is it's different yarns, and the outer layer is a carbon. It's all carbon yarn, and the inner layer is an insulating yarn.
Okay, so can the heat shield ever get too hot? That's G-Dog 16.
Absolutely, yeah.
And then it goes away. Just
That's
before
not
it goes
good.
away.
Right,
You don't have a heat shield anymore.
Right.
There aren't much left anymore.
Right, and some of the materials, the inside material, for example, when you get it too hot, it melts. You get glass. There's a lot of glass in it, and it'll melt and flow and collapse and get you thin. And you don't really want a heat shield that drips.
No, and
So,
that's
not so much.
And that's
Yeah.
what means test.
Test,
I'm
that's
going
why
to
we
go to
test.
Slayer X. Could you reuse the folding heat shield? Or is it a single-use kind of thing?
It's more of a single use. I mean, most of the missions we envision are going to another planet, and most
right.
of those are one-way trips. So we tend to design single use.
Okay. Does the fabric after re-entry stay flexible? That's from Chris.
That's a good question. It will still be somewhat. I mean, when it's deployed, we actually want it to be as close to a rigid heat shield and not be flexible because we want it to have that very predictable shape.
Okay.
So the material afterwards, I guess if we took it off of the ribs and everything, it would probably still be flexible, but
It's
at that point we don't care.
it gets a little bit stiffer
Yeah.
as you heat the carbon. It'll get a little stiffer.
So M. Gallon is asking, does the Adept fabric ablate during re-entry?
Yes.
It does. We do see layer loss. The carbon, now it doesn't, there's no pyrolizing going on because
Right.
there's nothing infiltrated. But what happens is the carbon oxidizes. That's the primary mode at which layers go away. And we knew that was going to happen, and that's why we have to do a special weave so that we don't get holes or anything.
Multiple layers.
The whole thing doesn't
3D
go flying
woven.
apart.
It was
Right, they
designed that way.
Right, you calculate
Everything is designed that
for
way.
how many layers are going to go away, and then you have structural layers below that.
No, and we saw tests early on where if it wasn't woven right, it would go away really quick.
That's the famous arc jet test.
Yes, we did arc jet tests on the
30
fabric.
seconds and it's gone.
Another question from Tombit asks, what past programs, Apollo Space Shuttle, have carried over to what you're designing now? I mean, obviously everything kind of builds on each
It all
other.
builds on it. Well, Apollo,
With
for Orion. Now the honeycomb in the Orion the Avcoat material flew on the first experimental flight for Orion. For the future flights, they're flying that same material but without the honeycomb. So it's now molded into blocks and machined and bonded onto the structure.
We talked a little bit about this. This is from Timbo. Do the sides of the spacecraft need heat protection too? We talked a little bit about
Yes, absolutely.
Yep.
In fact, we talked about for MSL and for Mars 2020, the material that's the heat shield material for InSight is on the back shell
As well.
to protect the back shell of the bigger, heavier, faster missions.
Okay.
So we definitely have to protect that.
Okay, the heat shields. Okay, somebody is saying the heat shields I weld on go on jets and are made of T or TI. I don't know.
Titanium?
Titanium. I guess.
Right.
All righty then.
Yeah.
They know what they're talking about.
They know. Hey, Pro Mitchell knows what he's talking about, and he's asking, "What's the reason your heat shields are made of carbon? Why carbon over titanium?"
Oh, well, I mean, titanium, great high temperature metal, but it just wouldn't survive these
Not high
type of extreme environments that we're seeing here. It would melt and go away in a second.
Right, on
Got that,
jets,
Pro Mitchell.
right. Even for the supersonic jets, they get warm.
Yeah.
Oh, wow.
And titanium would be enough. But these get hot.
Our rapid fire is getting rapid as we're about like 2 minutes left. It's KLC is asking what temperatures can it protect up to? So what are maximum temperatures are we thinking of here?
It depends on the material. Carbon can go easily above 3,000 Kelvin. So let's see, about 4,500 or well over 4,000 Fahrenheit. So it will get very hot. You get to a point where it stops oxidizing and it just starts going off as carbon. So it starts subliming, but it can get very, very hot. Other materials can't get that hot if they get above, the glassy materials get above about 1,600 Celsius. 2,500 Fahrenheit.
So if we can hit up one more question, this is from 4-year-old Ellie before we go into the outro.
Hi, Ellie.
How much cooler is it underneath the umbrella than on top? And then I got 1 minute to go. Let's go.
It's
It
pretty
is.
hot.
It's still pretty warm on the back side of this, so that's we have to pay attention to that. Not as hot as the front side, but still, you wouldn't want to touch it on the back.
Right, it's about
That's a good
400
question.
to 500 degrees difference.
And the point is to protect what's inside.
Yep.
Right.
So,
Right.
But folks, this is all the time that we have. We got to wrap things up. This has been NASA in Silicon Valley Live. It is a conversational show out of NASA's Ames Research Center in Silicon Valley, where we talk to the various scientists, researchers, engineers, and all around cool people here at NASA. And if you like that, we are on Twitch, YouTube, Facebook, Periscope. And once the show is over, we'll have on-demand video. So if you couldn't catch us live, don't worry about it. Go on to on-demand. We'll be able to watch that there, including next week up on NASA TV. Thank you so much to everybody for coming. This has been a super fun show. And like what we're looking at next, well, no, not next week because it's going to be Thanksgiving and I ain't going to be here. But a huge thanks to our guests. A huge thanks to the Twitch chat for everything you guys are doing. We'll be back on December 6th when we talk about SOFIA, the world's largest flying observatory in the history of airborne astronomy. And I am way past our outro. Until then, thank you for coming, everybody. We'll see you then.
Bye-bye.